Hi, everyone. Today's topic of discussion will be about LLM debates. So the goal of our project was to develop LLM alignment based on debates. So firstly, what is alignment? Alignment is a method that makes LLM reach some desired behavior. And debate is a simple protocol that helps to align LLMs with the desired behavior. So on the left side, you can see the simple example of a protocol. So in the first round, there are two LLM debaters that produce arguments. One of them is supporting the truth statement, the other is supporting the false statement. And in the second round, debaters take into account all the context from round 1 up to round k-1. And in kth round, they output another pair of arguments. And ultimately, there is a judge that outputs some preference of one debater and another debater. So on the right-hand side, we can see a simple example. So we have a question, and we have a first round of arguments. The second round is based on simply countering opponents' previous arguments. And ultimately, there is a judge. It can be like LLM judge or human judge, but as we want everything to be automatized, we decided to use LLM judge. And this LLM judge extracts probability logics of preferences. So there was like probability, in this example, probability of picking debater A is 67%, and probability of like preferring debater B argumentation is 33%. So this is a simple overview. And also, before I dive more into LLM debates, I'll give a brief overview of three simple or most widely used LLM alignment methods. So the first one is supervised fine-tuning. And advantages are that it's, well, simple. There is no need for a reward model. However, the disadvantage is that it requires a high-quality data set. The second method is reinforcement learning with human feedback. So that method is constructed in two stages. So in the first stage, we train a reward model. And in the second stage, we optimize LLM with respect to that reward model. So the benefit is that we optimize for certain reward modeling. However, disadvantage is the subjective and potentially biased reward model. So that's why DPO comes in. So in short, it skips reward modeling stage. And this is done by producing a formula for a reward model based on current LLM policy, reference LLM policy, and regularization parameter. However, obviously, the disadvantage is that it still requires preferences dataset. So now I will briefly talk about two pieces of related literature. As I mentioned, one of them is direct preference optimization. So the main contribution of that paper is that they produce a formula for reward model based on like current LLM policy, reference policy, and regularization parameter. So reference policy can be viewed as LLM. Reference policy is the baseline LLM. Yeah, so that's it. And obviously, this is optimized based on preferences. So we have two answers. One of them is more preferable. The other is less preferable. And based on the signal between the preference between two answers, LLMs are optimized towards certain behavior. The second paper that was related to our work is called Training Language Models to Win Debates with Self-Play Improves Judge Accuracy. So that says that when when debaters are optimized towards judge preferences, they're becoming better and better. And so the quality of debate improves. And that paper says that when the quality of debates improves, then it is easier for the judge to extract the truthful statement. And the main two points of that paper was that it applied DPO and its variants to two-round debates, and results were only run on quality dataset. And yeah, so that was like part of remarks given on open review, and these were like partially two reasons why this paper was rejected from ICML. So yeah, so basically in this paper, the experiments were run only on two-round debates, and results were only on a single data set. And that gave us direction into which we can improve the work. So coming back to our methodology, so we propose the following training algorithm. So we run LLM debate on n rounds. So basically, like two debaters, debater A and debater B, produce n arguments, and afterwards the judge makes the preference. However, yeah, so that's the first step. In the second step, we split n round debate into n chunks. Each chunk is optimized independently through DPO-based loss. And then we take the average of those losses, and this is the loss for the end round debate. Afterwards, the preference is determined by conditional probability from Hugging Face wrapper judge model. And the second thing is evaluation, and we evaluate both the judge, and the judge is evaluated based on accuracy in selecting truthful answer, and debater is evaluated by maximizing or like by measuring probability of being chosen versus reference model. And lastly, we evaluated results on GSM 8K and truthful QA.
Okay, so now I'll hop in. Now I'll discuss some challenges that we've faced during the development of the project. So one of the main important, I mean, one of the important part was the fact that we needed a framework for evaluating and running debates in kind of really fast way. That is, running the whole debates protocols on clusters is taking too much time, and we kind of needed some sanity check with simpler problems. So we've also faced some we also needed to find some optimizations for memory constraints. We needed to scale up with multiple GPUs, as well as creating some using parameter efficient fine tuning based on LoRa for tuning, and using some optimized images on the Athena cluster. And for local debugging, we've managed to create a toy problem that consisted of an arbitrary, like a judge that was deterministic and could be run locally. And we ultimately chosen a simple deterministic judge that just counted the number of letter L in the speech, and the preference of choosing this debater was proportional to the numbers of letter L in the speech. That was a really nice problem, really nice problem to sanity check our problems, because there are multiple tokens that consist of two letter L's. Letter L is kind of rare in the dictionary, but common enough to like see the training really catch up. And we've also based our debugging on the Llama 100K model developed by Delhi. Ultimately, we were able to run our local setup locally in around 4 minutes on Apple-based chips. Regarding datasets, yes. Oh, okay. Regarding datasets we used, we've used GSM 8K, which consists of mathematical questions, and Truthful QA dataset that have question and two possible answers. One is correct and the other one is incorrect, like a misconception or deceptive or another kind of wrong answer. And we've added some metrics like judge accuracy and win rate versus debate versus a baseline model. That is, we evaluated the trained model versus a baseline we created the trained model upon. And we've parameterized number of rounds in the debate and the length of the debater responses. And also we've created the we've implemented those DPO and IPO losses that Paweł talked about earlier. So jumping to the results, here you can see that this this graph shows that the accuracy, that the training is more powerful when the model we are using creates longer responses. So like the pink line you can see at the top is 256 tokens on truthful dataset. There you have also 128 and 32 tokens. So longer responses are necessary. And y-axis show the preference versus base model. Okay, so we've also tested GSM 8K dataset with both losses, and we show that you can generalize the training not only to Truthful QA, but also to GSM 8K dataset. That is in addition to quality dataset that the paper we are basing our work upon previously shown. We've also checked that the number of rounds have no significant influence on the efficiency of the debates. And this is also coherent with other works, from example from Google regarding debates. So you can see here there are just 3 different number of rounds are shown in the in this training. Yeah, and regarding conclusions, I've mostly discussed them while showing the effects. We've shown that we can use debates to different tasks. One conclusion that was not visible on the slides is that judge is almost always biased towards first debater. We didn't manage to like pinpoint the core problem with like core cause of this. It's not a problem. It's like kind of the way it is. And both IPO and DPO perform similarly, and the generation length is important when discussing debates. For the further work, we can look into different methods of training and weighing the respective runs, because yeah, and we also can, for instance, compare distribution of results to have a more statistically grounded comparison between algorithms. So, thank you.
I'm super curious if you have examples of these debates.
Yeah, we do. But like maybe I would be able to show, but it will take a couple of minutes. One interesting fact is that at the beginning of the training, when debaters were arguing with each other, they were supporting like their point of view. But after No. After some training steps, what was interesting is that the debate was beginning with attacking the opponent. So the strategy was changed from supporting themselves to attacking the opponent.
So the first one was also preferred, right, later on.
Sorry?
So the first one also was preferred later on, right, by the judge you mentioned.
That was, I think you're referring to the concept of this bias, so that the first debater has typically higher chances of winning the debate, which is also a bit interesting, but maybe it could be a bias or like a faulty of LLM.
Any other questions? If not, then thank you once again.
Thank you.
Thank you.